In this video we discuss sensitivity analysis for a linear program when we change the right-hand side of a constraint. We again consider the same example, but now we assume that the right-hand side of the first constraint changes from 4 to 4 plus delta. As a result, the vector b of right-hand sides becomes 4 plus delta 6, 8. Economically, this change corresponds to the change in the availability of the first resource. We initially assume that we'll have 4 units of this resource available, but now we allow the possibility of having a different amount of resource 1 available. Alright, so then if we look at the optimal tableau that corresponds to the previously optimal basis, the places where this change is reflected would be wherever b small appears, and in particular the most important part would be the right hand side here, which determines the feasibility of the previously optimal solution. Another place is of course the objective value, but that can be determined easily once we have the optimal solution. So the part that we need to focus our attention on is b inverse times b small. So we need to recompute this part right here and determine the range of delta for which this expression will still give us a non-negative value, in which case the previously optimal basis will still be feasible, and as a result, because the optimality criterion is not affected by the change of right-hand side, the previously optimal basis will still remain optimal. We will just need to update our solution by computing the new values of the right-hand sides, which will be given by b inverse times b small. Okay, so next let's look at how exactly we do it. So here we already have the optimal tableau for our problem, and we have b inverse put in the green frame here. So b inverse can be read from the columns corresponding to the slack variables, and the slack variables are x4, x5, x6 in our case. And again, it's important that we arrange the rows in the order which is the same as the order of variables here, and this is the order in which the columns of matrix B are specified. So we have B inverse, and we need to multiply it by the new B small vector. The result is this row times the column is 2, so the same value as what we had before for x1. Then multiplying the second row by the column that we have will give us 4 plus delta over 2 minus 1. So 2 plus delta over 2. And finally multiplying the bottom row by the same column, we'll obtain minus 4 plus delta over 2 minus 3 and plus 8. So 6 minus delta over 2. And this vector needs to be greater than or equal to 0 in order for the previously optimal basis to remain feasible and as a result optimal. So we obtain the following system that we need to solve in order to determine the allowable range of delta. We have 2 plus delta is greater than or equal to 0, and 6 minus delta is greater than or equal to 0. So from the first inequality we have delta is greater than or equal to negative 2, and from the second inequality delta is less than or equal to 6. So we obtain this range of values for delta for which the previously optimal basis will remain feasible and as a result optimal. If we want to express this answer in terms of the range for the right hand side value, then B1 is going to be between 4 plus delta values on the left and on the right. So 4 minus 2 is 2, and 4 plus 6 is 10. So B1 is between 2 and 10, and this is the range of values for the right hand side of the first constraint, such that the previously optimal basis remains optimal. So in these computations, we assumed that we had the optimal tableau, and all we needed to do was to read the B inverse from that tableau and then multiply by the new right-hand side, and then the range of delta is relatively easy to determine. So next, let's assume that we don't have the optimal tableau, we just know the optimal solution, and we are going to extract the matrix B from the initial problem data and then compute B inverse times the right-hand side. And here is our matrix B, so we just look at the columns corresponding to the basic variables in the initial problem data. And then instead of computing B inverse directly and then multiplying it by the new right-hand side, what we're gonna do, we'll denote B inverse times B by V. And then in order to find V, what we need to do is to solve a linear system BV is equal to B for V. Because when we multiply both sides of this equation by B from the left, this is exactly what we obtain. So then solving this linear system, we find exactly the same solution for our B inverse times B as what we computed before, and we obtain the range of delta between -2 and 6. So this is our answer. So next, what we're gonna do, we'll take particular values of delta and see what the new optimal solution is gonna be for those deltas. And we'll take one delta from within this range and the other one from outside of this range. So first, for delta within the range, let's take -1. It is within the interval between -2 and 6. And to compute the new optimal solution, all we need to do is plug in this value of delta in this vector right here, and this will give us the new optimal solution. Then we plug it in the objective to obtain the new z star value, so this is our new optimal objective value. So this case was easy because delta was within the allowable range and the optimal basis didn't change. But now let's look at a case when we have delta which is outside of the range. So delta is equal to 8, which is outside of the interval between -2 and 6. Then if we compute B inverse times B, we are going to get some negative values in the right-hand side. So in particular, if we do the computations, the new tableau that we're gonna get will be this right here. So this is the part that was affected by the change compared to the previous optimal tableau. And now we see that we have -1 for x6, and we cannot just proceed with the simplex iterations because this tableau is infeasible. So the corresponding basis is not feasible anymore. So then what do we do in this case? We observe that the row 0 still has non-negative entries because the optimality criterion was not affected by the change of the right-hand side. And since all the entries here are still non-negative, we can transpose our tableau like we discussed before and switch to the dual basis. And the corresponding dual tableau is actually feasible, and we can solve the dual problem in order to find the new optimal solution. So once you have this dual tableau set up, you just apply some iterations of the simplex method. So this is where we start, we apply one iteration and we get the new optimal solution for the dual in just one iteration. So you see, originally there was a negative entry in row 0 for the dual tableau, which was exactly the entry that caused problems for us for the primal problem that made the basis infeasible, right? So, but now entering this variable in the basis, we see that the row 0 entries become all non-negative, and we obtain the new optimal solution for the dual. And to read the optimal solution of the primal, what we need to do is to pay attention to the excess variable coefficients of the dual in row 0. And they're given by 4/3, 16/3, and 0. So these are the optimal values of our primal problem. x1 star is equal to 4/3, x2 star is equal to 16/3, and x3 star is 0, and the optimal objective value is 64/3.